Alright guys, welcome to lesson 2.11. We're going to talk about two special integration strategies today. The first one happens fairly frequently. The second one is kind of uncommon, but I have seen it come up here and there, so it's worth talking about. It's called long division. So let's go ahead and jump into these two special types of problems. We've actually already done the first one earlier in this unit, but I didn't really get you guys enough chance to practice it and stuff and focus on it enough. So that's what we'll be doing today, is spend a little more time on it. So splitting the numerator, example 1. So when it comes to these integration strategies, a big question you should be asking yourself at this point, we're going to focus on it too a little bit later, is how do you know when to use these strategies? And we're going to learn that in more detail on another day. But for now, how do you know when to split the numerator? When do we do this? Well, you're going to do it anytime. It's a possibility if your numerator has more than one term. Okay. Now, I hope you guys know what a term is. If not, it's two monomials that are connected by plus or subtraction. So for instance, and here's the basic idea. Here's the strategy. If you ever have a fraction where you have a plus b over some denominator that we'll call d, you can rewrite that as two separate fractions. Okay? And that's the strategy that we're going to use. Okay? Sometimes it's very straightforward. After you split it up, it's a simple power rule and you're all done. Sometimes it's a little bit more challenging. You have to integrate some other possible options into the problem. So the problem I picked, it is a more challenging one. And so it's going to force us to review some old stuff a little bit, but that's good. We need to review those things. But just know that just because this one is going to be challenging, it doesn't mean that all of them will be challenging. There will be some that are fairly simple, like that still use that strategy. So let's go ahead and take a look at this. Okay, so here's what this is the biggest part I want you guys to take away from this. The rest of it is just, think of the rest of it as a convenient opportunity to review. But here's the big takeaway I want you guys to have. It's in the first few steps. So the first thing is notice I've got more than one term in my numerator. And therefore, that's a good opportunity to consider the possibility of doing this. Now I'm saying consider the possibility because it's not always like this, but it's definitely an option to consider. But as you guys can see, I've rewritten it as two separate fractions instead. Okay? After that, we're going to treat these as two separate integrals then. So we're going to integrate this piece. That little smudge should not be there. Get rid of that. Minus, and then we're going to integrate this piece. All right, now that's right there. That is the new thing that I wanted you guys to get. That's our strategy, splitting the numerator. Now at this point, we're going to integrate each one of these things separately now. So that's it. By splitting the numerator, it creates two separate integrals, and you just do each one separately. Now, like I said, sometimes you end up with some pretty simple looking things. Like, for instance, you might have just an x squared there, and that's pretty easy just to apply the power rule. Sometimes you end up with more challenging and complicated looking problems. Now, these ones, I made it more complicated just because I want to review the strategies we've been learning. But let's go ahead and see. So now, for this first one here, how would I integrate this one here on the right? What would I do? Well, we're going to talk more about this on, I think, lesson 2.13. But for now, what I want you guys to notice is look at this power here. See how this power is one less than that power? When that happens, that's a pretty good indicator that you're going to do u substitution, where you make the bottom equal to the u. Okay? So that's what we're going to do for this half of the problem. So let's go ahead and do the derivative of u with respect to x is going to be 24x to the 5th. We're going to get the dx by itself. And then we're going to do our u substitution. After we put in this u substitution, I think you will see why I chose to go this route. Notice this is x to the 5th and so is this. They're going to cancel each other out. So anytime your power down here is 1 more than your power up here, you're probably just going to make the bottom the u, because after you take the derivative, the power is going to go down by 1 anyway, and they're just going to cancel each other out. Now, none of these things are always going to be the case, but what I'm telling you is what's usually going to be the case. Okay? Now, the 24 on the bottom, I'm going to factor that out as a 1/24th, and now I have 1 over u du. Now, how do we integrate that? Well, if I had a number here for a power like a 2, a 3, or a 5, if I had that, I would move it to the top, change the sign, and do the power rule. But when you have a 1 there, you can't do that. It won't work. This is actually an ln problem. So when you integrate that, you get ln of the absolute value of u. Now, I'm not going to put my plus c on here. I'll explain why in a little bit. But for now, we have this. And then, of course, we're just going to go ahead and put the u back in. My u was, what was that? It was like 4x to the 6th power plus 9. I think that's what my u was. Now, in this case, just so you guys know, technically, the absolute value bars are not necessary because this is an even power. So no matter what you plug in for x, the x part's always going to come out positive. This is positive, and this is positive. So everything's always positive. So technically, we don't really need the absolute value bars on this, and I can just write it like this. It's not a big deal. You can leave the absolute value bars, but technically, that would be the simplest way to write it right there. Now, we're not done, though. Remember, that was only half of that problem. The other half was the other side, right? So we split this integral up into 2 separate integrals, and I just did the integral on the left. Now we have to do the integral on the right. Now, notice this. Look at this. This power is not 1 more than this power. So the u substitution thing where you make the bottom a u isn't going to work. Now, we have seen some problems kind of like this, and what I would encourage you to do is think for a minute. What strategy do you think this might look like? What pattern does this seem to fit of all the integration strategies we've been looking at? Well, the only one that we've really looked at that fits this pattern is the things that have arc-trig functions. Arc-trig functions. And in fact, this one would fit the arc-tangent pattern because we have 2 perfect squares here. Okay, so that's kind of tough to identify, but there it is. We just need to identify what integration strategy is. And like I said, on day 13, we're going to talk about how you can get a little bit better at identifying each strategy. But for now, this fits an arc-trig pattern. Now, in order for it to fit the arc-trig pattern correctly, we want this to be a square, not a 6 power. So what would I put in the parentheses so that after I square it, I end up with 4x to the 6th? Well, that would be 2x to the 3rd. Okay? And whenever we do that kind of a strategy to make it fit the arc-trig pattern, we are going to do u substitution, where u is equal to the part that's in the parentheses. And so if I replace these items here, we have 6x squared is on the top. We have u squared plus 9 on the bottom. And if I replace the dx with du over 6x squared, lo and behold, those cancel out, and I have now a nice, perfect arc-trig integration pattern. All right, so when you do an arc-trig integration, we have 1 over a, and a is the square root of this number, so that would be 3. Arctan of u over the square root of that number again. And once again, we need a plus c, but I'll get to that in a second. So for now, we have a 1/3 arctan of, and my u, I believe it was 2x to the 3rd, if I'm not mistaken. And there's that. So now I've integrated both sides. The left side gave me this, and the right side just gave me that. Now I didn't put a plus c. Why didn't I put a plus c? Well, technically you could have. You could have put plus c here, and you could have put plus c here. And what the plus c represents is it just represents some unknown constant number. So what do you get, though, when you put one unknown constant with another unknown constant? Well, when you put one unknown constant with another unknown constant, you just end up with another unknown constant. So there's no point in writing it twice. You really just need to write it once. Okay? But something that we might be apt to miss is not only did we split these things up, but when we did you guys notice that these things are being subtracted from each other? Okay? So I'm going to come down here, and now that I've integrated each one of these things separately, I'm going to put a big subtraction sign between them. Now, that's kind of ugly looking, so I'm not going to write it like that. I'm going to rewrite it so it looks more appropriate. Minus 1/3 arctangent of 2x cubed over 3 plus c. And that would be my final answer there. Okay? So we only need the c one time. So now, like I said, I would consider this problem to be a little bit more challenging because the integrations were not really quick and simple things. They required u substitution, and they required 2 different strategies that you had to remember from the past, okay? But just so you guys know, it is possible to end up with an example like splitting the numerator that's pretty quick and easy. Like, consider this one, for instance. If I had this, you don't have to write this, but you can. I'm not going to do the whole problem, but basically we have more than one term in the numerator, so I can split this up, right? And so if I integrate these separately now, I have that, and this one can be reduced. And then all I would do is just change this to a -2. I would change this one to a -3. And from there, you just do the power rule where you add 1 and divide by that number. So this one would be substantially less work. Okay? So the point is that splitting the numerator is not always this much work. Okay? But it can be. I just wanted to give you guys a great review of a bunch of things that we've done. But the real strategy here is, if you ever have more than one term in the numerator, you could split that up into 2 separate fractions and integrate each piece separately. Okay? So now I'm going to let you guys practice one of those. All right. So go ahead and try this problem. See what you can do. Go ahead and pause the video. Go as far as you can. If you can at least get through the first few steps of applying the strategy we've been talking about, that's great. If you can actually finish the problem and take it all the way home, that's even better. So go ahead and pause the video and see what you can do. All right, so this is, I would really like to have seen everybody gotten at least to this step where you split it up into two separate fractions, cosine squared over cosine plus sine over cosine, and then you can make that two separate integrals. Now you'll notice that for the one on the left, the cosine squared over cosine just became cosine, because cosine squared means you have two cosines in the numerator and one cosine in the denominator, and so the one in the denominator would cancel one of the cosines off the numerator, and so you'd be left with one single cosine left if you reduce that fraction. The other one doesn't simplify. Now, for the integral on the left, that one is going to simply be, for the one on the left, the integral of cosine is negative sine. But the one on the right, we're going to have to do some u substitution. Let me write down my answer really quick for the integral here on the left. For the one on the left, that's going to end up being sine x. The integral of cosine is sine x. And once again, I'm not going to put my plus c here yet because we'll just do that at the end. But let's focus on the right side. We're going to let the u be equal to the denominator, which is cosine x. And then I'm going to find the derivative of that with respect to x, which is negative sine x. And then we get the dx by itself and we end up with this. Then we do our u substitution. Oops. And we end up with sine x over u, and then du over negative sine x. Now the two sine x's cancel out, but that negative in front of that sine on the bottom, we can't just ignore that. That's a negative constant multiplier, so I'm just going to take the negative and put it in the front. And after I do that, we end up with 1 over u du. And once again, that's an ln problem, just like on the last one we did. So when you integrate, you get negative ln of the absolute value of u, and u was cosine. Now you have to keep the absolute value bars because cosine is not always positive. Sometimes cosine gives negative values, sometimes it gives positives. So you do need to keep the absolute value bars because they do make a difference this time around. So that's the integral of the one on the right, and we already did the one on the left. So if we put those together, sine x being added to a negative ln of cosine x, you can just make it minus, because when you add a negative, it's the same thing as subtraction. And then don't forget your c. So here would be our final answer. A good way to check your work, if you're interested, you don't have to, but a good way to check your work would be to take the derivative. So use what we learned in Unit 1 and see what you get if you were to take the derivative. So if I were to take the derivative of this, for instance, I would get cosine x. If I were to take the derivative of this, I would get 1 over the absolute value of cosine x times the derivative of the inside there, which is an absolute value problem, so we kind of have to remember how to do that. The way that you take the derivative of an absolute value is you do something to this effect, I believe. And then you multiply it by the derivative of the inside, which would be negative sine x. So here's the derivative of the ln, here's the derivative of the absolute value, and here's the derivative of the cosine. It's like a double chain rule, the eggshell, egg white yolk problem. Anyway, so the absolute values you can just get rid of, and so we're left with cosine of x minus a negative sine of x over cosine of x. Those just add together, right? Because double negatives make a positive. We need a common denominator, so I'd multiply this one by cosine x on the bottom and on the top. Cosine times cosine is cosine squared. You don't have to do this, by the way. I'm just showing you guys how you can check your work by working backwards. And then combining them because they have the same denominator. And we're right back to where we started. So when you take the derivative, it should take you right back to the original problem. If it doesn't, then something went wrong with your integration process along the way. Okay? All right, so that's one of our strategies, splitting the numerator. Let's go ahead and take a look at our next strategy, which is something that involves a pre-calculus topic known as long division. So we need to review how to do long division. It's been a little while since you guys have done it. So here's how it works. Whatever is in the numerator is going to go inside of the division bracket. and whatever's on the bottom goes outside. Okay? Now, before this long division process will work, you need to make sure that all the powers are accounted for. I'm going to write some steps here on the side. The top goes here, the bottom goes here. I'm going to call step 2, all powers are needed. And then in parentheses, I'm going to put zeros, and you'll see why. Here's what I mean by that. I start off with a 2x to the third. Now, what's the next lowest power? That would be x to the second. But notice there is no x to the second here. But it's not okay to have that missing. And I'll explain why in a minute. But if you're ever missing a power, whatever it starts with, you should have the next power down after that. So that would be a 2. So to get that, you need to put a 0x squared in. Then the next one would be x to the first, which we have. And the last one is a constant, which is an x to the 0, which means we don't have a power there. So I've got all my powers there. 3, 2, 1, none. Same thing applies out here. It starts with x squared, so the next lowest one should be x to the first, but I don't have one. So I need to put a 0x in there. So now you may be asking, why do we need to do that? Well, when you're doing long division, if you don't have that, you're going to mess things up because along the way you need to combine like terms. And if you don't have all these powers present, your like terms won't line up correctly and you'll probably miss something. So it's a good idea to make sure that all your powers are there. If they're not, just put them in there with a 0 in front. That's like saying, well, it's not really there, but we're giving it a placeholder. All right. From there, we do the long division. Okay, and that's where my steps will get a little bit more difficult to explain, but I'll do my best here. So, long division. What we do is we ask ourselves, how many times does x squared go into 2x cubed? Now, another way that you could ask that question is you could ask yourself, what would you have to multiply x squared by to get 2x cubed? So think about that for a minute. What would I have to multiply x squared by to get 2x cubed? Well, you would need to multiply it by 2 to get a 2. And then you would also have to multiply it by another x because it's only x squared, but we need x cubed. So this is what I would multiply it by, and we're going to put it up there. So I'll write my first step over here. What would you multiply the first term outside the brackets by in order to get the first term inside the brackets? And you just put that on top of the brackets when you're done. Put it on top of the brackets. All right. The next thing we're going to do is we're going to take that term and multiply it by all 3 terms, and then we're going to put them underneath. So 2x times x squared gives me 2x cubed. It should match because that's what we wanted to happen. Then 2x times 0x. Well, 2 times 0 is 0, and x times x is x squared. So I end up with a 0x squared term there. And then 2x times 1 is 2x. So you're going to multiply the answer you got from part A by the outside polynomial and put under the other one. So we have blah, blah, blah here. You're going to put your answer right here. Okay? So now what we're going to do is we're going to subtract all that. That means we're going to change all the signs. So change change, change. Now, it doesn't mean you're always going to make them negative. I said change the signs. So if you actually have something down there that's already negative, then it becomes positive. All right. But in this case, all of mine are positives, so they become negatives. So I'm going to get rid of my positives there. And so for part C, I'm going to say change signs. And then part D, what we're going to do now is we're going to combine these like terms. So 2x cubed minus 2x cubed goes away. 0x squared and 0x squared doesn't matter. That just goes away. And then negative 8 and negative 2 makes negative 10x. Bring down the 5. And so combine the like terms and bring down your terms. Okay? Now, I'm a little bit disappointed. I kind of wish this one had more stuff, but what you do at this point is you repeat the process if necessary. Okay? And in other words, what do I mean by that? You're going to take, you have to ask yourself, what would I multiply this first term by to get this first term? And then you just repeat the whole process. I should have put repeat step 3 if necessary. So you would ask, what would I multiply this by to get this? You would put your answer up here. You would multiply it, put it underneath, subtract, combine, all that. You would repeat those steps again. But notice I said if necessary, because you may not need to. And how do you know when you're done? You're done when this power is bigger than or bigger than this power. So since this 2 is bigger than 1, we are done. Okay? So step 5, we need to write our answer, and here's how you do it. You have your divisor, which I'll represent with the letter V. You have your dividend, which I'll represent with the letter D. You have your answer, which is the quotient, and then you have your remainder at the bottom. The way that you write your answer is like this: quotient plus remainder over divisor. Now hopefully this isn't the first time you guys are seeing this. This all should be reviewed from your pre-cal or algebra 2 classes. Because this could be a little overwhelming if it's the first time you saw it. If it is, we may have to help you practice it a little bit. But if it's not, then hopefully it's just a review. But here's how you do it. You have your quotient, which is the number on top of the bracket. So for me, that's 2x. And then we have plus. And then we have the remainder. That's the part that is down here at the bottom. So for me, it's negative 10x plus 5. And then we have the divisor on the bottom here. And that's the one inside, the one outside the bracket. So it's going to be x squared plus 1. I'm not going to put the 0 there, because this 0x, because the only reason we had that was so the long division would work out, but I'm done with that. So in my final answer, we don't need it. And we have that. Now you guys might be thinking, oh, that probably wasn't fun, and you might be thinking, gosh, I guess I kind of remember that. So why are we learning this in here? Well, it's actually something that can help you with integration. Okay? So we're gonna learn how to do that right now. But before we actually start the calculus, I think I want you guys to be able to practice this a little bit. So I think what we'll do is we'll treat it more like a guided practice where we'll do it one step at a time. So here's the first thing I want you guys to do. I want you guys to do the first 2 steps. And that's just setting up the problem. So pause the video here, and when you unpause it, you will see the solution. Do just the first 2 steps. So the first 2 steps was to put the polynomial that's on top inside the brackets and the polynomial that's on the bottom outside, but also to make sure that all the powers are accounted for. So this one starts at 2, so the next one after that should be a 1, and then none. We were missing that 1 power in the middle here, so we had to put that there with a 0. Same thing with the top. The top goes from 4 to 1, so we're missing powers of 3 and powers of 2. So I had to put a 0 power to the third and a 0x to the second to make sure that all my terms are accounted for. All right, so now we're on to the next step. Next step was 3a. So go ahead and see if you guys can do step 3a. Pause the video. When you unpause it, you'll see the solution. So the answer to step 3a was x squared, and it goes up there. How did we get that? We asked ourselves, what do I multiply this first term by to get this first term? And the answer is x squared, and you put it on the top. Okay? All right, go ahead and do step 3b. Pause the video, and when you unpause it, you'll see the solution. Step 3b was to take your answer from 3a and multiply it by all three of these, and then put your answer right there. So that was step 3b, and that's what you should have gotten by doing that. Okay, go ahead and pause the video here, and I want you guys to do steps 3c and step 3d. I want you to do 3c and 3d. All right, and so now we have this. So step 3c was to change all the signs in the bottom equation there, or bottom expression, and then to combine down. Now the first two just kind of cancel out. In the last one, when you do 0x squared and negative 2x squared, you end up with negative 2x squared. And then you bring down the other two terms. Now, step 3e, or maybe I just called it step 4, I think. Step 4 was to repeat step 3 again. So we're going to go back and do all this again, and I'll give you a head start on this one. So we're going to do start with 3a again. And how do I know that I need to keep going? Because this power is not bigger than this power. They match. We stop when the power out here is bigger than the power down here. But in this case, it's not bigger. It's actually equal. So we are going to keep going. So now what do? We're going to do step 3a, which is where you ask yourself, what do I multiply this by in order to get, and here's where it's different, that. So go ahead and do step 3a and put your answer up here. What you guys should have gotten here is they both have an x squared, so they're good there. So all it needs is a negative 2. So I'd multiply it by a negative 2 is what I would multiply by in order to get that first term to match the other first term. Go ahead and pause the video here, and I want you guys to do step 3b. Step 3b would be to take your negative 2 and multiply it by all three of these, and then put your answer here. And so that's going to give me negative 2x squared plus 0x minus 4. Go ahead and pause the video here and do step 3d. Step 3d is to change the signs. So we have plus, minus, plus. And then add down. Pause the video here and add down. So if you add down, these will cancel. You have a 1x minus a 0x. You end up with 1x again. And then the 4's cancel. Now, you'll notice that this power is less than this power, so we are done. The last thing that we need to do is write our answer. So see if you can write your answer correctly now. Pause the video and see if you can write your answer, and when you unpause it, you'll see the solution. And there it is. So we have the quotient plus the remainder divided by the divisor. But notice you don't put the 0x in there anymore. And so there's our answer. All right? So that's long division, but we haven't really seen what this has to do with integration yet. Okay? So now we're going to go ahead and do an integration problem. Now this is the problem that you guys just did. Okay? Notice that we have x to the fourth plus x minus 4 over x squared plus 2, right? We just did that. So when are we going to use this long division strategy? That's a good question. It's a little difficult to recognize, honestly. So I mean, technically for this problem, you could have split this up into 3 separate fractions, right, and did the last strategy. That's not uncommon. But here's an option for you. Something that makes this one a little bit different than the last one is, let me back up a little bit. When we had these situations, yes, we had more than one term in the numerator, but look at the powers. The biggest power up here is 5, and this one's 6. Now let's compare that to the next one, the one that we're on right now. For this one, the power on top is 4 and the one on the bottom is 2. Notice that the power on top is bigger. So here's would be my suggestion. You would want to consider using the long division one whenever you have a polynomial with a bigger power being divided by a polynomial with a smaller power. So, in the example that we did in the beginning where we split the numerator, the bigger power is actually on the bottom. Okay? But when you're doing long division, the time when you want to do that is if the bigger power is on top. All right, so now we already did this problem. So the first step when you see the situation, a polynomial with a bigger power on top of a polynomial with a smaller power, is the very first step you want to do is to do some long division. Now we already did that, right? And here's what we got. We got x squared. What did we get? X squared minus 2 plus x over x squared plus 2. That's what we got in the last slide, right? So the first step when you see a polynomial with a bigger power over a polynomial with a smaller power is to do long division. And that takes a little bit of work, but once you get there, you're going to rewrite your integral. I'm not changing its value. I'm just rewriting it using long division. It's the same expression, it's just written differently. Okay? It's written as a quotient with a remainder and a divisor instead of a top and a bottom fraction. But those two expressions are actually the same. Now what we do is we integrate each piece separately. So what do I mean by that? We're going to integrate x squared. Then we're going to integrate 2. And then we're going to integrate this one. So we're going to do each of these pieces that are separated by pluses and minuses separately. Okay? This one, simple power rule. You're just going to add 1 to the power and divide by that number. This one, all you do is put an x next to it, so that's cool. The next one is going to take a little bit of work. Okay? It's a u sub problem. Notice that the power on the bottom is 1 less than the top, and we talked about how when that happens, you do u substitution. And you guys might be feeling a little overwhelmed right now with all these strategies, but I just want to comfort you once again. Don't worry, we're going to spend a day where we're not learning anything new, but rather we're actually just taking the time to learn how and when to do each of these strategies. Okay? So don't despair. Just walk through this miry place with me for now, and then we will spend a day talking about how to know when to use each of these strategies. So right now I have x cubed minus 2x plus the integral of x over x squared plus 2. All right? Well, let's go ahead and do this piece now. That's what we need to do. So as we said, we're going to do u substitution where the u is the bottom. We're going to find the derivative of u with respect to x. We're going to solve for dx. And then we're going to do our u substitution. Okay, so as you guys can see here, The x's are going to cancel, and I'm going to take that 2 out in the front so it looks like this. And when you have a 1 over u, that's an ln problem, right? So now we have the x cubed minus 2x plus, we just did all this work, and we're going to find out that we have 1/2, and when we integrate this, we get ln. So 1/2 ln, absolute value of u, don't forget your c. We're almost done. We just need to replace the u with what u equals. And in this case, do we need the absolute value bars? The answer is no, because we have a square plus 2. And that will always be positive. So you could also write it like this. And then we're done. Okay? So, what's the strategy? The strategy is when you have a polynomial being divided by another polynomial, and the polynomial on top has a bigger power than one on the bottom, you start with long division, and then you integrate each piece separately, and you're good to go. All right? So, throwing at you guys here. Now, you guys are going to start from the very beginning. You're going to start by doing long division. So I want you guys to begin this process, and step 1, I want you guys to pause the video here, and I want you to rewrite this integral using long division. Whenever you are done, unpause the video and you will see the solution. All right, there you guys have it. So there's your long division off on the right side of the board. If you want to check your work or check mine, you're welcome to. But there it is. And so if I rewrite it, my quotient is x squared plus 6x plus 18, so we write that first, plus the remainder, which is 59, over the divisor, which is x minus 3. And so we've rewritten it. All right? The next thing we're going to do is we're going to integrate each piece. Okay? So now the last piece, you can wait on that one. But go ahead and integrate the other 3 pieces first. Pause the video. When you're done, you can check your work. So if you integrate x squared, you get x cubed over 3. If you integrate 6x, you get 3x squared. If you integrate 18, you get 18x. And we haven't integrated the last piece yet, so I just wrote it as an integral still. All right, so from here on out, I'm going to let, I want you guys to see if you can integrate this. It's a u sub problem. The bottom has a power of 1. The top has no x at all, which means that the power is 0. So the top is 1 power less than the bottom, and when that happens, you do u substitution. So go ahead and solve this problem letting u equal x minus 3. Pause the video, and when you're done, you'll see the final and complete solution. So final answer's down there at the bottom. Like I said, we're going to let u be that. Solving for dx, we get that. Doing our u substitution, we get that. Take the 59 out. It's another ln problem, so we get that. And replacing the u, we get our final answer. And on this one, you do need to keep the absolute value bars because x minus 3 could turn out to be negative at some point. So there it is. That's the final solution. I believe that does it for the day. Let me take a look here just to be sure. Yep, that was it. All right, so happy homeworking, and we'll see you guys next time.